All right, let's start with lecture number 5. Today we're going to talk about memory and peripheral buses. But first, a couple of announcements. You might have asked what these DFMs are all about, like the FreeDFM service that we use. DFM stands for Design for Manufacturing. So this is basically a test and a check of your PCBs telling you if this board can really be manufactured. So what you saw is sometimes you had errors that were a little bit bogus and they fixed them themselves, so they were not showstoppers. Other times they told you like these are actual showstoppers, which means that something is really odd or strange with your PCB design, something that they don't feel confident about that they can actually manufacture. So let's look at two of these violations. One of them is a solder mask clearance violation, right? Like probably a lot of you had these solder mask clearance violations. The other one is a insufficient spacing violation. Who thinks insufficient spacing is a problem? What does it actually mean?
That's always layer.
Exactly.
So if you look at this layer, they gave you a plot here, right? What does it mean? Yeah?
Meaning that someone wrote in copper.
Yes.
Instead of
So in this particular case, somebody wrote text onto the copper plane, right?
And ignored my comment, 3 comments in my class. I emphasized that several times.
One of the big problems with this is if you have text on this copper plane, Altium lets you do that because sometimes you want to do that, right? Like sometimes you want to put text on your copper plane because it can look nice, especially if it's gold plated. In this particular case, I don't think it was done intentionally, and what happens is that you now have traces that go over the trace, and sometimes they could short together. So if it says insufficient spacing on one of your copper planes, very, very bad. Because it means that sometimes they can guarantee that it won't get a short in their manufacturing process, right? Even though your design might be very clear and there might be like 100 mils in between, no, not 100 mils, but like maybe 2 or 3 mils in between your traces in your Altium designer, well, when they go into manufacturing and use etching tools to basically get the copper away, it could be that it's so close and so small that the copper just doesn't come away and then you get a short, right? So this is an error that you can't ignore. Now, what about this one here? Insufficient solder mask clearance. What does it actually mean? Anybody? What does it mean? Yes?
means your solder mask too close.
Exactly. It means that the solder mask, that's that green stuff that's on top of the PCB, it gets too close to one of your pads or openings that you're supposed to have. So they can't guarantee that the solder mask will be actually outside of the pad, but it could happen that it's actually on top of your pad. Now, that said, sometimes you actually want to do that. So what happens in the design is the following. Like if you look at it in the physical structure, you have your PCB that sits here, right? This is FR4 material, which is fiberglass. That's the stuff that's in between the sandwich. Up on top, you have a copper trace, or a hole, or something like that. And then on top of this, they put the solder mask to basically make these things not conductive to the outside so you can actually touch them without actually touching the metal. So what happens is, if it's just a trace, you get covered up like this. Right? That's what we want. Now, if we have a hole somewhere that we want to solder to, you preferably want the solder mask to stop before the hole. Or else, it could happen that this solder mask goes on top of the hole and it does something like this. And this is not very good because this can then lift off and the solder mask can come off, and they don't want that. In addition to that, we now have this gap on here that you have to fill with solder, and sometimes you have to go inside of it, also not very good. Yet again, sometimes this effect is actually needed. For example, for BGA type of devices, which are ball grid arrays, where you have the chip, and on the bottom of the chip you have a lot of small little solder dots. There you actually want something like this, so that these solder dots go on top of the solder mask, that they help them to align and stay up on top there. But most of the time, this is not what you want. So that's why FreeDFM tells you, well, your clearance is so close, you basically went right to the edge here, that we can't guarantee that we don't go on top of it. They need a clearance between your copper that you have here and wherever the solder mask should stop. Is it a showstopper? No, because sometimes that's what you want. But in this case, they just warn you, we don't think this is what you really want. Any questions?
So we should fix something like this?
You don't have to. You can let them make it. It's not a deal breaker and see what comes out. Yes?
How do you fix them?
This particular one, what you can do is you can go in, click on the hole, and I think that was one of the things I did back in the day when I made this footprint. I have a solder mask override that I put in, and then say I want a 0 mil clearance. Just increase, like take either the check mark off, and it will automatically have a clearance around it. Or if you keep it on there, there's the override of 0 mil. You can change to 3 mil that they need as a minimum, and then you should be fine. Yes?
Did you reduce that, or did you set it to 0 mil expansion to avoid solder mask slivers?
Probably. So what can happen is if you actually make an expansion, it expands it that much that there is no solder mask in between these two pads anymore. And then it becomes more difficult again to solder, because what can happen is that you bridge these two pads. Yet again, you can imagine it like if you actually look at the PCB, if these two coppers are so close together and there is no filling in between, it's very easy for solder to go in here and bridge these two. But if there is actually solder mask in between these, bridging them is avoided more often than not.
Excuse me.
Yes?
Then we need to exit the solder mask on the hole.
I'm sorry?
I mean that when we need to put the solder mask
Uh-huh.
on the hole.
You only put solder mask on top of the hole if you want to cover it up. So that's when you don't want to solder anything to it. Then you can put solder mask on top of a hole. And what's that usually called is called tenting. So oftentimes for vias, if you look at actual PCBs, sometimes you can see via holes that go down, but they have solder mask on top. So what they did is they tented these vias with a solder mask because they know they won't solder to them, so why not just tent them over? And the boards look nicer, and you also have less chances of shorting. At the same time, again, you can't probe your board anymore at these spots. Like if they're actually open, you can take a oscilloscope probe and just bonk, probe the signals that go through. So there's a trade-off that you sometimes have to do. Okay, 2 more errors that I saw very often. Who can tell me what the difference is between these two pictures, except that one of them is a bigger one chip than the other? I want to hear from somewhere over here.
Pad exit.
Pad exit, yes. Look at the lines over here. This all works electrically. It's fine. This will work, this board. But it's just very clear. If you look at these boards, this one over here looks a lot nicer, right? If you as an engineer look at a PCB and you see something like this, you just feel that the person putting this board together didn't really care that much, right? He was either in a rush, didn't have much experience. So it's okay, this works. But if you get a board like this, you just know, okay, this person actually cared. The board looks nice if you look at it. It's not completely wrong. I'm just telling you, like, try to do it this way, not that way. Yes?
So I think that's the actual picture of my board.
A lot of people had this board that way.
I was having a really hard time with the snapping feature.
Yes.
And like, I thought that is what it was expecting.
No.
I didn't even think that was conceivably possible to do.
It is. So what?
Start in the pad.
Yes.
Oh, you
Start out off
you
from the
don't
pad.
route to the pad.
Exactly. And even if you route to the pad, if you hit spacebar, it actually changes the angle of which it goes into the pad. So sometimes you are at a 45-degree angle and you hit spacebar and it actually aligns it properly. But yes, oftentimes for pads in Altium, it's easier to route away from them than into them. So what I oftentimes do is I route out of a pad, go close to the other pad, stop at the location where I wanted to, go to the other pad and finish it that way around. But then yes, again, hitting spacebar helps you a lot in aligning and getting the right angle into it. Any other questions on PCB layouting? If not, please submit your boards by this Friday. What we try to do is, or I contacted Circuit Graphics and they are aware of all the PCBs that are coming in. So what they will do is they will hold off of actually starting them on And then we will probably start them on Monday, and hopefully we can pick them up by the end of next week, and I can go down there and pick all the boards up, and then we can hand them out during the class. So not all of us have to drive down there, pick them up, and come back home. Make sure that you write University of Utah in your email so that they know that this is for this particular project. Maybe mention the class might help. If I know 7 or 8 already submitted them, is that right? Some of you have submitted it. Did you put University of Utah in the email? Yes? Okay. At the same time, I have all the order IDs, so I can also send them the order IDs on Friday so that they can put them all together and make sure that we have all the boards. Hopefully nobody else from the University of Utah has the same idea and uses them right now. Okay. A couple of more things. What are the contents of a typical linker script? This is the linker script that we used in last class. Very simple, right? Where we have just RAM. We have one text section, we put that into the RAM, and then we are done. So what's the content of a typical linker script that you will use later? Looks something like this. A lot more complicated, a lot more content, right? We have, again, the text section up here, but check out what all the different things are that are put into the text section. There's a lot of different things that libraries sometimes want. Like if you look in here, there is like the GNU warning libraries, glue7t, and a lot of other things. Then down here, we put all that stuff into RAM. Down here, we have the data section, we have the BSS section, etc., etc. So if you ever look at one of these linker scripts that you later on will use, this is more like it. A lot more complicated. Okay, fun and easy minute quiz. It should be fairly easy this time. Okay, this time let's do tail is the minute quiz. It's tail. I'm sorry. In this particular case, the answer is one word, so it's really easy. It's not word. All right, ready? Good. 1 minute, sharp this time. Thirty more seconds. Five. And pencils down. I'm sorry.
When would you want to change the linker script, or like, I would think there's something like when you're writing the BSP or something on the code, right? It's not very often that we need to
Yes. No, usually you don't need to touch the linker script, especially not if you get an environment for a microcontroller that's already set up. But sometimes if you start a new environment or a new project or a new platform, you have to write the linker script yourself. But what you oftentimes can do is you take somebody else's linker script and change it the way you need it. So the only things that you oftentimes have to change are how much RAM is there, how much ROM is there. And that's about it. That's the only way that I usually touch a linker script. That's why I don't really know all the details of that particular linker script. There's so much in there. But I just copy one of them and then adapt it and change it to the way that I need it to.
But I can think of a case like, let's say, if I porting some program that used to run on PCI, you can port it on ARM, then maybe I need to go.
It could be. Yes, it could be. All right. So today we're going to talk about memory mapped I/O a little bit more, and then we go into bus architectures. This time we're going to talk about a real bus system, the bus system that's actually used on the ARMs. It's called the AMBA. In this case, we look at the ARM APB and the ARM AHB Lite buses. Last time we talked about memory. Today I got a question that I'm not entirely sure if that's the answer, but sometimes you can address the individual bits of a register sitting in memory by using one of the words. And that's in these locations here. If you have an address in the peripheral bitband alias, these aliases point to memory locations in the peripheral section. So the peripheral sections are all down here. This is the bitband area for it. So if you want to read up on details on that, search for bitband on ARM Cortex M3s, and it will tell you what this particular case is. So in the SmartFusion documentation, that's where they talk about it. Yes?
What benefit would that give you over just using a map, like an ANDed mask or an XOR mask?
Sometimes you really don't want to touch other bits. Even if you AND it, or if you, for example, read something out of it, sometimes you really only want to go and read one bit and not touch any of the others. That's when you would go into this particular area.
Okay, so yeah, I guess with a mask you read it out.
Exactly.
Map and stuff and then bring it back.
Yes.
This will be one instruction done.
Correct. I rarely use it. Oftentimes they make the register maps such that you always have to write into something to clear a bit, or you read a bit to actually get the status out. You will see about it. Like sometimes you have 3 registers to do operations on more or less the same background register that they're actually using. So exactly for this case, if you want to clear one particular bit, you write it to one memory location. If you want to set one particular bit, you can write into a different memory location without having to change or touch or read out that particular register. Did that make sense, what I just said? So if not, it's a very important concept. So imagine you have a register in the background that toggles your I/O lines, right? So we have a 32-bit register with a lot of slots in here. Assume you can read and write this register. If you read it, you get the status of an I/O line. If you write into it, you will change the status of that I/O line. Okay? So how do you make sure that you only change, for example, bit number 30 without having to go and change any of the other registers?
You create a mask.
You can create a mask, yes. So the problem is you can't just write one right-shifted, left-shifted by 30 into this register, right? Because what would happen is you would set all these registers to 0, bits to 0, and that bit to 1. So you just changed the output of your I/O lines. What if you don't want to do that? Well, the first thing is you read this register out, get the status of all the different bits. Then in code, you flip this particular bit and write it back into that register. Made sense? So you read the status first, flip the bit of that status, and write it back. Then you know that these bits have not changed. Now, yes?
The mask still seems a lot easier.
Okay, how would you apply the mask?
like and with a bunch of ones, and then my bit, whatever I want to change.
Sure, but you just read out this register, right?
Oh, yeah.
Same thing.
It's the same concept, right? Like, yes, flipping this bit in that read out status register, you apply a mask and do stuff with it, yes. Right? So now, oftentimes they have a trick. What they do is they have one of these registers in the background, but they then declare eraser. What they do is instead of just one of these registers, they have 3 of them. Where one of them will be the status, one of them will be the set, the other one will be the clear register. So they are all 32-bit wide. And what happens is, if you want to clear one of these bits in this register, you write into this memory location and set the bits here. And then only the registers that you actually set in here will be cleared in here. So setting would mean you write a 1 in here, and then you make sure that this bit would, for example, be cleared. Or if you do it this way, so you set 0, 1, and the rest all zeros, then you would make sure that this bit will be cleared to 0 in the actual register. If you want to set a bit, you could use a second register. Whatever is set in here will then be set and applied to this register. And the status register would be, if you want to read the status of this register, you could read it out. So oftentimes, what then happens is that this register would be a read-only register, and these would be write-only registers. If you read from these registers, you get garbage back, most of the time, or just zeros. But there is no meaning behind them. So that's a different way of how they oftentimes make access to registers available, without having to go and read the whole status out. The other one is using the bitband area, where you can address individual bits of certain memory locations. Okay? Yes?
You mean we have three another register for every register?
2 more. But that's not always the case. That's just sometimes how they implement, in some peripherals, how they implement certain techniques. Yes. So for example, they use the status as the storage register, and then applying and changing things on that register, you use these 2 different registers to write into certain bits and to clear certain bits themselves.
I think this is more easier.
This is also how it's often done. So, especially for things where you can get problems with writing and reading into it. All right. Is for everybody clear how you would get something out of memory in assembly? How you read something out of memory? What assembly instruction would you use? LDR. Load from a memory location into a register, right? That's how you go and get data out of any of these memory locations in there. Yes?
Are there nice assembly header files that define this human readable aliases?
No, that's when you use C. So you can do the exact same thing in C. Now, how do we tell C where a variable is located at? We give it the address, exactly. So what do we have to do? What type of variables do we have to use? Pointers. Exactly. Pointers are addresses in memory, right? That's all pointers are. So this is how you can address a memory location using C. What you do is in this case, we hash define a, what are they actually called? A constant to a certain memory location. Then we define a unsigned integer 32, so 1 word, of a pointer named reg. And we set this to the typecast of this memory location. So basically, this pointer here will now have this value, right? So now you can do operations on this pointer with the star and the and signs like this. If you want to read it out, or if you want to write into it, you can do a star reg, or equal this particular constant here. What does this do? Exactly, it will read this memory location, right? Because we have the star of the pointer, it will actually operate on the memory location, not on the pointer itself. So it will set this pointer address to 4, or it will OR the content of this register with this, and then we AND it with the mask of it. So we actually will set it to 0. We will, in a second, see how this is translated into assembly. So it really makes clear of what's really happening in this particular instruction. There are a couple of things that you usually use in embedded systems that you don't always see in regular C code. We have modifiers const. They make a variable constant, so you can't modify it, and hopefully your compiler would tell you that this is a non-modifiable variable that you just used and tried to modify. Oftentimes, these variables will be put into flash memory, so they don't need to sit in your RAM, which is more valuable than your flash. Registers, you can tell the compiler to really try to keep a variable in a register. I have rarely seen it, but sometimes it makes sense if you want to optimize a certain code. If you know that you will access this variable a lot, so you can actually keep it in a register so it doesn't have to go load and store it all the time from RAM. You can declare something as static. If you do that, you basically make a variable global, so it's also available outside of the scope of your C code where you have this variable declared in. And you can have something that's called volatile. This is exactly the opposite of a constant. It basically tells the compiler that this particular variable points into memory where the memory content can change without you knowing. So the compiler will not try to optimize a variable that you have declared as volatile, because the compiler can't assume that the content of this variable changed. Who has used volatiles before? Okay, you will use it a lot in the next couple labs, because basically every memory location of a peripheral is declared as volatile, because you don't know when these things change. So the compiler needs to know that variables that point into peripherals shouldn't be tried to be optimized if you try to keep reading from it. So let me do an example. Assume you have a counter that counts in one of the peripherals and just increments, and all you want to do is read this counter and output it as a printf on the serial port. If you have a while loop where you read the same variable all the time and output it on your serial, as a printf on your serial port, what could happen is that your compiler is smart enough, sees that you're accessing the same memory location all the time, and just optimizes it away, does one read of the memory location, and after that just outputs the register all the time. Well, that would defeat the purpose, right? Because you wanted to go and really read that memory location. So what you do is you declare this as a volatile, and then you know it will go and actually read that particular memory location all the time. Yes?
So I'm trying to make understand the difference between const and register, because if I were to implement const in assembly, logically I would just put it into some register that I would not want to modify.
No,
To me,
it would not be in a register. It would certainly not be in a register.
So where does it get stored?
It gets stored in flash. So if you declare something as const, it will go into the data section of your linker script. And the data section is usually in ROM, which is a memory location. And what would happen is, yes, it would eventually get read from that memory location into a register to do operations on. But it's in ROM and not in RAM, because you can only read from it. You will never be able to write back into it unless you do a more complicated operation on the flash memory. Okay. Bus architectures. Here's actually the link between your C assembly and what's really happening in the background. Okay, let's look at this particular example. We have a memory location that we defined as rec_foo. We declared an unsigned integer 32 as a register pointer and set it to this memory location. We now do a star rec plus equal 3. Get together in teams of 2 or 3, discuss of what you think happens in this particular memory location. or with this particular instruction. When this instruction gets executed, what happens on your system? Okay, what's your thoughts? What happens? What's the first thing that has to happen? Actually, what do we do? What does this do, this particular thing?
Adds 3 to the value of that.
Adds 3 to the value of the address?
At the address.
At the address, exactly. It modifies the memory where this address is pointing to, right? So what do we have to do first? What happens? In order to execute this particular C function, what will happen on the microcontroller in assembly? Yeah, at the blue line, this guy. What is this going to be translated into?
What's the value?
I heard it, a load, right? We load into, let's say, R1, wherever foo points to. Right? It goes, gets its memory location, then what?
Add 3 to R1.
Add R1, 3, last, store it back. Exactly. Now, don't get me wrong, it could be that some of the notation here is wrong, but I think I'm not sure if they have to be W's or not. I don't think actually they have to be. But that's what happens. They get translated into a load, an add, and a store sequence. So if you now go one layer down, now we know which instructions they are. So the load instruction will be put into a bus access, right? Because now we want to go and get something from the memory, which sits on the bus. It's not inside of our core. So it will get put into a bus operation. The CPU will drive the address of the register onto that bus. Then it will indicate that we want to read this particular address. There will be some handshaking that occurs like last time, and then the register content will be put onto the data lines of the bus, and the CPU can go and get the data, put it into a register. Right? The add instruction, we add 3 to the register that we have inside our core. And then the store instruction is exactly the inverse again. We're going to put the register address onto the bus, put the data onto the bus, tell it's a write. There is some handshaking that happens again, and then that data gets stored back into your flash memory or RAM in this particular case. Make sense? So the magic in here that we have is still this handshaking. And that's actually some of the key that happens in your bus architectures. There are a lot of different handshaking mechanisms that happen these days. So for example, we have on system-on chips, you have memory and peripherals. They most of the time sit on something like the AMBA, AHB, or APB bus, which we'll be looking at in this particular lecture. You can have NAND flash, which can be off-chip, where we oftentimes have a NAND flash interface. There are standards for these interfaces. Or you could imagine you have external memory, external RAM, right, on your computers. Yet again, there are different kind of bus architectures. There are different handshaking. In this case, JDEC, JSD79 or 792F, and there are a bunch of other ones that it can run RAM with. If you look at our microcontroller or at a modern microcontroller, there are a lot of different bus systems out there. Oftentimes, or legacy buses that get talked about in embedded systems courses are the ones here on the side, which are external memory interfaces, so how you hook up to NAND flashes and SDRAMs. Down here, we have a lot of different serial and parallel buses to talk to, for example, SD cards, SPI buses, I2C, other serial buses, parallel buses. These are all external buses that usually go off chip. In this particular lecture, we will talk about internal buses. In this particular case, the AHB bus matrix that connects our core to fast, high-speed peripherals. And we will talk about the APB bus, which is the peripheral bus that connects the core to slower speed peripherals that don't need as fast access as some of the other peripherals that sit up here. For example, up here on the AHB, we have RAM, ROM, we have a DMA, and sometimes they have high-speed Ethernet buses that also sit on Ethernet buses that sit on the AHB. On the APB, oftentimes you have all the slower speed UARTs, timers, etc., that sit on there. So this is the focus of this particular lecture. We will talk about the AHB and the APB, and we will look at a lot of different bus diagrams. So bear with me, they can be a little bit boring sometimes, and sometimes they all seem the same again. I will try to really point out what the differences are between them, and maybe you have to go back later on and actually look at them and see what the details are of the different things that happen in these buses. So why do we have so many buses? Well, because we have a lot of different architectures. There's master versus slave, internal versus external, etc., etc. So get together in teams of two again and talk about what are some of the trade-offs that you have to make. So why do you have master versus slave buses? Why do you have internal, externals? What are the advantages or disadvantages? What would you have to change in a bus architecture, for example, if it were an internal versus an external bus? Let's do 2 minutes, and then we try to make a list on the blackboard. All right, so what are some of the trade-offs that we have to make in bus architectures? Why do we have that many different buses? So let's go first to the internal versus external buses. What are trade-offs that we have to play?
If it's external, you can access it from outside, different controller, versus if it's internal, you have to go with
You have to go to?
If it's internal, it's not that easily, you can't just have any other slaves out there.
Okay, so internal buses usually are permanently hooked up to something. It's not a extendable bus, correct? Yeah. What else? What's a huge difference? Why would you have some buses that, for example, the AHB, why do you run the AHB only internally? A lot of wires, right? Internally on a chip, you can have a lot of wires going back and forth between the different peripherals. You can have them 32-bit wide with 32-bit addresses, which would be 64 pins. Now, if you want to push that out of the chip, you need 64 I/O lines hooking up to it. And that's not all, especially not in the AHB case. The AHB, I think, has about 128 different lines that go back and forth to make stuff really fast, right? But as soon as you go external, you want to reduce the number of pins that you have. Make sense? So that's some of the big trade-offs that you have. At the same time, speed. Internally on your bus, you can be a lot faster than as soon as you go outside of your chip, you have capacitance that starts to play in, you have to go through pads, you have to make sure that wire length starts to matter, so you have to take care of these kind of things. You can have synchronous versus asynchronous buses. What's the big difference? What's an advantage of an asynchronous bus? Sorry? You don't need a clock, exactly. Yeah. So if you have two systems that are apart from each other, they don't need to share a clock. You don't need to have a clock line going actually to the other guy. It's asynchronous. At the same time, synchronous buses are usually faster than asynchronous buses because you have the clock line. It's a lot easier to deal with synchronous buses than with asynchronous buses because you have a clock that can drive your digital system directly. Right? So what are the two trade-offs that we have in the AHB and the APB? The AHB is what's called the Advanced High Performance Bus, and the APB is the Advanced Peripheral Bus. Both of them are part of the AMBA, or the Advanced Microcontroller Bus Architecture, which is a bus architecture that ARM defines and publishes out there, so people can actually start using it in their own peripherals that they put in their chips. So this is an open definition that ARM has out there. AHB is for high performance, has pipelined operation, we will look into that in a second, has burst transfers, can multiple bus masters, so it's a multi-master bus. It can have split transactions. While the APB is lower power, it's latched address control, has a simple interface, and is suitable for most or almost all peripherals, many peripherals in this case. So in the case of our Smart Fusion, this is a block diagram of the Smart Fusion chip itself. What you can see is, where is it? Up here, that's the Cortex M3. It's connected to the AHB bus matrix. On the AHB we have the DMA controller, an APB bridge, the external memory controller, Ethernet MAC that's sitting on there, it sits on the AHB, has another APB controller here. We have our FPGA that sits directly on the AHB, so you can have you can write your own peripherals that sit on the AHB bus. We have memory, non-volatile memory, and the RAM that's on the AHB bus. And then on the APB buses, we have 3 different APB controllers. On one of them, we have the analog compute engine, where the ADC and the DAC sits. We have, on this one here, we have the serial interfaces, SPI, UART, I2C. And over here, we have the supervisory module with a 32 kHz clock and a real-time clock on it. And then back here, we have another APB bus bridge that connects to another set of serial connectors and the 2 timers that are provided for you. You can see we have, oftentimes there's a bus matrix in the middle, and then we have APB controllers that sit on the side to actually do the APB transfers out. So let's first look at the ARM AHB Lite version. We're not looking at the AHB directly, we look at the Lite. The differences between the Lite and the AHB is that AHB Lite is a single master mode. It doesn't offer multi-master, which makes a lot of things a lot easier. It supports still burst transfers. It's a single clock-edged operation, has non-tri-stated implementation, and it has a configurable bus width. So what does that mean? What does a non-tri-state configuration mean? No drive high impedance. Remember how last time the data lines, we had to either drive from the initiator or from the receiver, and you have to make sure that they don't collide? Well, in the AHB, that's not the case. You have basically a data line that goes from the master to the slave, and you have another data line that goes from the slave to the master, depending on if you do a read or a write. This is the whole architecture of the AHB Lite bus, and all the different signals that you will start to look into. So in your VHDL code, once you see stuff like H clock, H reset, H address, HW data, and a bunch of these control data down here, then you know you're dealing with a peripheral that actually uses the AHB bus itself. It's fairly complicated, right? If you look at this. Especially, imagine now many of these lines. So for example, the H address line, I think it's 32 bits down here. We have the size is 3 bits, burst 3 bits, proto is 4 bits, transfer is 2 bits, master clock that's 1, 1, another 32 bit here. And if you go up here, read data is another 32. So overall, we have a lot of different traces that go through this bus itself. Trying to push this outside is almost impossible. There are so many different lines. But internally on your chip, it's fairly easy to deal with these kind of buses. So what are the different signal definitions? The most important ones are H clock and H reset. H clock is the bus clock that basically tells us how fast things are going. The reset is a reset signal to the bus that would reset all the peripherals that are sitting on the bus itself. So if something goes wrong, you can hit the reset line. We then have the address itself that will address our bus, 32 bits. We have the write data. We have a whole bunch of different control signals. We have the write indicator, which tells us if it's a read or a write. Remember, write equal 1 is a write, write equal 0 is a read. We have the size, which will tell us what size of the transfer we want to do. So it could be a byte, half word, or word transfer. We have a burst indicator that tells us, we will look into the burst actually in details, how many bursts that we want to read. So we can increment at a certain number and do a very quick read from a memory location, then increment the reads automatically. You have the protocol that we are using. We have the HTrans, HMasterLog. Most of these we will almost never need to worry about. And on the slave, what comes out is we have the read data. So if you read something, it will be pushed out onto HR data. We have a ready indicator telling the master when it can go and pick up the data itself. And we have the H response, which is a response from a transfer. Did the transfer work out? Yes, or if there was an error internally in the peripheral itself. So this is an indicator to the microcontroller if my transfer to the peripheral worked or not. And oftentimes, if it didn't work, you will get a memory fault or a bus fault or something like that on your microcontroller. Quick conventions on timing diagrams. If we see something like this, then it's usually the clock that just goes up and down and up and down. We have a transition from high to low, looks like this. If we have a transition where in the meantime nothing happened, so it was a high and then became a high again, they have a little tick in there, which means that something could happen in this particular location before the line comes back up again. If we have a line that goes like this, so there's a line on top and at the bottom, it means that at this point the bus has been stable and no changes have happened on the bus itself. If the bus is high impedance, you usually see like when it goes from a stable mode into a high impedance mode, that it's a line in the middle. We have the bus changes itself, so if it's a multi-bit bus, you have something like this, and then there's a new value sitting on the bus. And if it transitions from high impedance to a stable bus, you have this particular symbol here. This is important because now we will look at a lot of these guys. These are bus diagrams. And in this case, it's the AHB read transfer and the AHB write transfer without wait states. Anybody know what a wait state is? The name says it, but what does it mean?
You're just waiting for data, right?
Exactly. It's when the peripheral is not fast enough to handle the particular transfer, you have to add wait states until the data is actually available on the bus. Anybody has an idea when this could happen? When would a peripheral need a wait state? Yes?
When a peripheral will be in a wait state?
Yes. Well, what would happen is the master wants to read from a location, and then the peripheral tells him, hey, wait, not so fast.
Peripheral can't keep up with the master request.
Sorry?
Peripheral cannot keep up with the master request.
And when would that happen? How could this happen?
ADC.
If you have to read a peripheral that's slow, right? In your case, you said an ADC, yes. Or if you, for example, have to read out of flash memory, the flash memory is not fast enough sometimes. It cannot keep up with the speed of your bus. So what the peripheral has to do is it has to wait for a couple of clock ticks until the data has been read out of your flash memory and put back onto the bus. So wait states get added if a peripheral can't keep up with the master clock itself. In this case, AHB always has first an address phase and then comes a data phase. So the first clock tick that happens, the address has to be set up. The address has to be valid on the falling edge itself. And the next time we have the data phase, and the data has to be valid on a read on the rising edge again of that second data phase. So your peripheral has time, once it knows that it has to be addressed, it has time up until the next clock tick to actually set up its data. On a write, what has happened is that we again have the addressing phase, And then in the data phase, the data has to be already valid at the falling edge, before the falling edge of the next location itself. So this is how you oftentimes see, like, if it's a data phase or if it's a read or a write. The main difference is you have the H write is low, and here it's high in the address phase. Make sense? Fairly easy so far. All right, let's look what happens if we have a wait state in there. In this particular case, we have two wait states. What happens is H ready gets pulled down at the beginning of the data phase. So what we know is that the master has to keep the address that he pushes out on the next phase, has to keep this one and wait until the data is ready. Then we pick up the data from A, and we will see what happens with this particular case right now. Okay. So with one wait state, very similar. Again, we have the transition down here. H ready gets pulled down. Peripheral tells us that we have to wait. The data has to be held constant until it's picked up again in the next clock tick. Valid data over here. All right. What happens if the wait state has to extend? So I talked before that we have the bus is pipelined, right? So the nice part is we want to really speed up transfer on our AHB bus. So what happens is we have the address phase of phase 1. In this case, we do a write. And then in the next phase, we can do a read from B, right? But the data from this write is not available until the next clock tick. But the address is already set up for the next particular case. So what you can see is this is staggered. We have address, data for B. In this case, it's actually up here. Why is it back here? Because we had a wait state inserted in here. So what happens is A is the address. We indicate we want to be a write. So the data is on the write bus available here, gets written into that address at this particular clock edge. We set up a read from B, but the peripheral isn't ready, so it pulls down the ready line. We have to wait and keep actually address of C, which will be the next operation, into a write, constant over this whole data phase. The data for B will be read over here at this clock edge, at which point we set up the next one, which will be a write on C, which happens down here. As you can see, something is happening on each and every clock tick if there are no wait states. And if there is a wait state, the next transfer has to be held constant over that transition until the wait state is done, and then the next transfer happens. Right? So the address stage will be pulled over the data stage of the one access that had happened previously. So far, so good? Yes?
So the master's controlling the top 4 and the slave is the last 2? Is it?
Correct. No, actually, the master controls this, and this, and the slave these 2.
And what happens when you have multiple slaves on there?
With multiple slaves, they will be based on the address.
Okay.
So the address memory location will be telling you where you are at, which slave will be selected.
Was this the one not tri-state behavior?
Yes.
So how does it handle?
There is actually another signal, the H-select signal, which will select your peripheral, and there is an actual there is a decoder that decodes the memory location and has a select line out to different peripherals that will tell you, this address matches you, you're selected now, you should do an operation. And they will then drive the write data into that one. Okay, transfers can have 4 different types. We have the idle type, where nothing happens on the bus. We have a busy state, which will tell a slave that the master is busy and it has to wait. We have a non-sequence transfer, which means that this new transfer has nothing to do with the transfer that just happened previously. And we have a sequence transfer, which means that this transfer is related to the one that just previously happened. So how do we use this? Well, the non-sequence and sequence are used in burst transfers. In a burst transfer, what happens is in the first addressing stage, we say it's a non-sequence with a certain memory location. In this particular case, what we did is we say the master is busy, so the slave has to actually wait to address this state, and it will keep the data just in here. So it's busy, 24. It waits with the data for 24 until it happens in the next sequence step here, sequence, here, sequence, data. Was that right? No, sequence data over here, because there was a wait state. In this particular case, the burst is an incremental burst, and what you can see is that the address always increments by 4 unless you have a busy state up there. So what's the advantage of something like this? I mean, you could do this all with non-sequence addressing mode, right? Where you just tell the peripheral 20, 24, 24, 28, 20C. Why would we indicate that this is an incremental burst to a peripheral?
Instruction memory.
Sorry?
Maybe instruction memory.
Instruction memory? Could be. But what can the peripheral now do, knowing that we are in an incremental burst?
Set itself up for the next read.
Yeah, you can do optimizations in your peripheral. For example, if we know the size of our read, we could go and get bigger chunks out of flash memory. Or if you have to access an external bus system, we can go and get bigger chunks from there to optimize the bus transfers. And that's all what bursts are actually used for. And there are a lot of different bursts. So, yes?
In previous slide, the non-sequence and or busy or sequence is related to address. For example, when the address is the same, we say the one is busy.
Yes. Busy basically just told the slave that, wait, we will repeat this again. Like,
Non-sequence, what does it mean?
non-sequence means it's not related to what happened before. It's basically the start of a burst, in this case. And then it tells it, we are busy on the transfer. So basically the incremental didn't happen, and then the increment happens in the next one.
And sequence means that
Sequence means it's in a sequence of addresses, in this particular case. And then it points to what the type of the burst is on how the sequence is set up. And there are a lot of different types that can happen. So you can have different sizes of bursts and different types. You can have byte transfers, half word, word. You can have double, 4-line, 8-word line of transfers. So these different types of bursts will tell the peripheral how many bytes I actually want to read from you, in what size of chunks I actually want them on over the bus. In addition to that, we have different types of bursts. We can have a single one, that's just like one quick read. We can have an incremental one where the incremental, we know that the memory address will increment, but we don't know for how much we will increment. We can have a wrap 4, which means it's on a 4-byte boundary that our wrap happens on memory location. We will look at that in a second. We can have an increment 4, which means that we will increment 4 times from the first memory location that I give you. Similar then, we can have wrap 8, increment 8, wrap 16, increment 16. So what does this wrapping all mean? This is an example of a wrap 4 transfer. What happens is the first one is a non-sequence, read from 38. We get a wait state down here before the data is available over here. Then we get to 3C, but because it's a wrap on Verdaline, what happens is after the 3C location, we go down to 30 and then 34. So this is our burst of wrap 4. We started reading at 38. Once we hit 3C, then we go down to 30 and 34. Yes?
Does the CPU have burst instructions?
Sorry?
Does the CPU have the memory, the burst memory reader, right?
It usually happens automatically.
It's just the DMA that
Mhm.
does this kind of
Yeah.
Okay.
Increment 4, different from before. We have 38, 3C. Now we increment to 40 and 44. We can do a similar thing with wrap 8. This time we go 34, 38, 3C, and then drop down to 20, 24, 28, 20C, 30. So it's basically just a modulo 8 on the last digits on your address that you do with these wraps. Interestingly now, you can also change the size. So if you say you have a half-word size transfer, what happens is the address is incremented by 2 bytes, because half-word is 16 bits, so this is how you go through your bus now. Or You can also change it in between. So what you have is we have an increment of half words. In this case, we do a change and go over into increments by words, and you can see how the addresses change. One of them is non-sequence sequence, non-sequence sequence sequence, etc., etc. Sorry?
Does that imply it's two different instructions when you do the
Yes.
non-sequence?
It's how stuff happens on the bus differently. Any questions to the AHB bus so far? Yes?
When you wrap, the address that you started on seems to be kind of in the middle of all the address values that you wrote. Why is that?
Good question. I'm not entirely sure. In what case you would actually use this? Sometimes maybe the way how you address memory when you read out of the code space, you want to start at this location and then you wrap down. I actually I'm not entirely sure why they have these wrap locations, but it's a possibility that it's in there in the AHB bus. Okay, the bus that you will deal with more often is actually let's jump over to the APB bus, because this is the bus that you will actually use in your labs. It's a lot easier, trust me. Fewer signals, it's lower cost, it's lower complexity, but it has also lower bandwidth. It's non-pipelined. So you don't have multiple transfers happening at the same time during the same clock tick. The signals that we are dealing with are fewer. We have a clock, a reset line, we have an address, a select, an enable, a write, a data, a read data, a ready, write data, ready, read data, and a slave error. Some of these signals are similar than before, but we don't have this whole pipelining and bursting anymore, which will make everything a lot easier. What we have, though, is the bus idle state. We have a setup state instead of an address state, and we have an access state. The smallest bus, they look a lot simpler. What we have is we have the clock up here. We then have the address and the setup phase that happens at this particular clock edge. And we then have the setup in here. We have the access phase in the next clock tick. So no more staggering of address, access, and data that we had for the AHB. It's always a setup phase, access phase, you're done. You do have a wait state still. So APBs can wait and can tell you to wait. In this particular case, it's the ready line. So what happens is we have the setup phase over here where everything gets set up. We set up the address on this clock edge, if it's a read or a write, and which peripheral gets selected. On the next one here, we get the enable phase where this line gets pulled up and basically means you can now go and access your data. We have the data down here. We can pull the line down telling it that, hey, wait, this data hasn't been picked up yet until the line gets pulled up, and then in the next phase, the access phase is done and the data disappears. The bus gets let go and the next phase can happen over here. A read transfer with no wait state. Again, set up on this clock edge. This is the setup phase where everything has to happen. And at this falling clock edge here, everything has to be ready. In this particular state, the access state, the data has to be actually ready at the falling edge of the clock itself. A read transfer with a wait state example, again with a setup, wait state, and access phase. And you will learn all about this particular bus in lab number 3, where you will also hook up to parts of the APB bus through some of the pins. Yet again, we don't have enough I/O lines to actually get the whole bus system out to go and look at it, but at least some few lines you can go and look at and measure the difference to actually see what's really happening with the clock and the data at the select lines and enable lines on there. All right, any questions?